Yeah, I can do that. I guess Ranjay isn't here. So we're going to hear a talk from Yue. So I think almost everyone here knows Yue interned with us here twice and did like excellent projects here both times. And he's done a lot of other cool work in his PhD involving language priors and other like vision language work, which I think he's going to tell us about here today. So we're excited to have him, and I'll hand it over to you.
Okay, great. Thanks for the introduction, and hi everyone. Welcome to my talk. And today I will talk about language priors for visual intelligence. And it's great to have prior in my job talk title. One important goal of my research is try to build visual intelligence that can benefit the real world. So one story I usually use to motivate myself is in Botswana, an African country, there are only 15 radiologists in the entire country, but there are over 2.6 million people there, and over 2,000 patients will die for TB every year. TB is a disease that can be diagnosed from chest X-rays, and if we can apply AI systems to help those people to better diagnose those diseases in time, a lot of people's lives will be saved. But the question is, can now those AI systems ready to be deployed in those critical domains? Recent years, we've seen great success of applying AI systems in general domains. We do this by scaling up our data, like include a lot of data and train a black box model, which do not have a lot of priors, like transformers, which do not have a lot of inductive bias. And but such way in critical domains like healthcare or robotics, we have much smaller data in scale because of some privacy issues or some cost issues. It's hard to scale up the data, and sometimes those data contains biases. If we train such black box model on those biased data, we may just lead to a model which has limited generalization ability, which is hard to deploy in critical domains. One evidence here is during pandemic, researchers want to build X-ray classifiers to help identify COVID-19. So the setup is like this. We have a lot of data in hospital A, like in a developed country, as our in-domain training data. And we want to deploy such model in outer domain in a different hospital, like hospitals in Botswana. And we found such COVID detector, they can achieve very high performance in hospital A. But when tested in hospital B, it will drop a lot. And when we visualize models' attention, we found those models are not looking at the lung area, but focus on some corners of those X-rays. This is because those data contains a lot of bias. Different hospitals using different format of X-rays, using different device to take X-ray. And model is taking those spurious correlations as shortcuts to get a high performance for in-domain. And compared to how radiologists making diagnose, they are relying on some knowledge priors, rely on this like ABCDE rules to learn how to interpret X-ray. And in the context of robotics, we hope our robot can be applied in like residential environments like living room, bedroom, but also they can be navigate in some other environments like gym, daycare. However, due to the data scarcity issue in robotics, it takes very long time and costly to build those simulated environments. So previous work mainly focused on residential environments. And if we test the agent trained on those residential environments, they may not work well for some novel environments like gym or arcade. So here's a zero-shot object navigation success rate pre-trained on Proxor. It can achieve very high performance on ISO because they both on residential environments. But when tested on novelties or with some novel environments, the performance will get close to random. So if we can give agent a prior on like how those environments will looks like, we can better mitigate those generalization performance. So in this talk, I will propose try to incorporate language priors in help developing those vision systems. And we start with the motivation that language and vision, those two modalities represent the same physical world. So given the same physical entity in the world, we can get the 2D image representation to train the vision model. And we can also get some textual descriptions to train our language model. And the recent success of large language models, we scale up the data and get a strong model which encode the word knowledge for our physical world. So we hypothesize whether we can use the priors we learned from language data to help design better, more advanced visual intelligence. And how to apply language priors? So we propose two different ways. First is from the model structure angle. Like we propose to use language priors as part of model's architecture using this bottleneck structure, try to improve the trustworthiness and the robustness of vision systems. And the second line of work is try to use language model to generate synthetic visual data to improve the data efficiency of some vision task. And in this talk, I will introduce two sets of work. First, we use language as structure in this language bottlenecks, try to improve the interpretability of vision systems. We also show that those bottlenecks can be a more robust medical AI systems. And for the second set of work, we will show how can we use language-guided synthetic data to improve the data efficiency for vision language models and embodied AI. So let's start with interpretability. So there have been a huge amount of efforts try to understand or try to explain black box models' behaviors. So the mainstream of work is called post hoc interpretable method, which is we keep the black box architecture intact. We don't want to change it because it's good for performance, but instead include another black box module, try to understand the model's behaviors. One famous work is called GradCam, which we will compute the gradients of the model given some predictions and backpropagate the gradients to the input image to visualize the attention map. So like given the prediction as a chickadee, we can see that such method can highlight the head of the bird, which is pretty good. But if we change it to an irrelevant class, like a coffee maker, it still highlights the similar regions of the image. So it's hard for human to tell the difference between those two different predictions. So the main challenge for such method is those explanations are not faithful to models' behaviors. They are incomplete and sometimes misleading. So what are the alternative solutions? Here we show the inherently interpretable models. And one such model is called concept bottleneck model. And here we will try to incorporate some language into the model structures. So different from traditional end-to-end black box, which is given input image and output a label. What happens in between is a black box. And concept bottleneck models will try to insert a human annotated concept layer. So those concepts are some human readable, interpretable descriptions or some attributes like the color of the bird, the shape of the bird. And the input image will first predict over those concepts to get some concept scores. And finally, use this concept scores through a linear layer, we can make the final label prediction. And such system can give us local explanations. We can look at those concept scores to know which are the most relevant concepts for this image. And after training the linear layer, we can also get some global explanations. This linear layer will learn the association between the class and concepts. And we can know what the model have learned from data, what are the most important concepts to recognize some objects. However, concept bottleneck models is hard to deploy in the real world because of two challenges. First is it is hard to scale because it requires extensive human efforts to annotate those concepts, and sometimes requires human experts in annotating those concepts. And second, previous work have shown that concept bottleneck models perform worse than their black box counterparts. And in our work, we will try to address those two challenges. And here we present our language model guided bottleneck, LABO, which we will, instead of ask human to annotate concepts, we will prompt a large language model to generate those concepts. We can achieve this by simply prompt a large language model with the class name as input, like describe what a chickadee looks like. And language model will return some useful textual information that can help us to recognize this object. And here we don't need a human to annotate each image to get some concept grounding functions, but instead we use a pre-trained image text alignment model like CLIP to ground concepts and images. So using this way, we can automatically build concept bottlenecks for any image classification task. And such system is so simple, it can be readily applied to different classification tasks. So we test Labo on like common objects like ImageNet and some fine-grained objects like flower or food, and like human action recognition, or even some specialized domains like skin lesion images or satellite photos. So we compare Labo with a black box model, which is our baseline, the linear probe. So the main difference between linear probe and Labo is they both use the same clip to extract the visual feature, but the linear probe will use the black box visual feature as the input for the linear layer. While for our language bottleneck, we will pass through the features through our bottleneck to get interpretable concept scores as the input for the linear layer. So our model is interpretable. And we show the model's performance in both few shot and fully supervised settings. And the x-axis is the number of shots, which is the number of training images for each class. And as we can see, the model, our language bottleneck can outperform linear probe at a few shot. And with more training data, we can achieve competitive performance. And our performance gain at fewer shot is come from these language priors. Because we incorporate language knowledge into the system, the model do not require a lot of training data to achieve a decent performance. And here we show some qualitative examples to show the top concepts for each class. And those top concepts is ranked by their weights in the linear layer. This is come from the global explanations for CBN. And from the linear weights, we can know which are the top concepts that has high impact on recognizing such objects. So you can see here, those top concepts are semantically meaningful to those objects. So to sum up, in this work, we show we can use language models to automatically generate high-performance concept bottleneck models for interpretable image classification. So feel free to interrupt me if you have any questions. So with such language bottleneck, are they ready to be applied in medical domains? Before that, there are some other challenges in medical domains. First is the data in medical is quite small in scale and sometimes has biases. There are some uneven distribution over some demographic variables, which will make a model easily to overfit on the data. And also we identify a key missing piece for existing vision models for medical images that lack of priors for how to processing medical images. And all those lead to that those models are very sensitive to domain shifts in medical applications. And there's such news that AI system can detect human race from the medical images, but doctors cannot identify such demographic variables from the image. So in this case, we need more robust models for medical AI. And next, I will talk about this knowledge bottleneck model, which we try to incorporate knowledge priors from medical documents to improve the robustness of some medical AI, medical image tasks. So to quantify the robustness, people usually introduce this adversarial splits, try to incorporate some confounding factors into the data sets. So we can have our in domain, which is the training and validation data, and outer domain is for test. So during training, we confound all the positive cases as female and all the negative cases as male. But for testing for the outer domain, we will switch this combination, like all the males are positive and all the females are negative. So a robust model should perform well on both in-domain and outer domain and should not use sex as this confounding factor to learn the solution. So we can evaluate a black box model's performance on such data set, and we can use other confounding factors like age or race, like black people and white people. So we found a fine-tuned vision transformer, they can achieve very high performance for in-domain data. But when tested on outer domain, the performance will decrease a lot. This is because those vision transformers did not learn how to classify positive and negative cases for those diseases, but rather taking shortcuts using confounding factors to achieve high performance for in-domain data. And we also we want to know why in medical applications, those deep vision systems is performing so bad and easily overfit on biases. So we found the lack of priors. So there's a previous work shows that those vision backbones like vision transformer or convolutional neural network, they are good featureizer even when entirely untrained. So we can show this by using a baseline here, which is we use pixel values from the images as a feature. So there's no priors in those features. And we use that for the logistic regression to do some image classification task. And we can also grab some vision backbones like CNN and VIT. To be noticed, they are untrained, they are randomly initialized. We use them as featureizer to get features, also through a linear layer to make the prediction. And we show that on natural images like ImageNet, those vision backbones, even when entirely untrained, they can still be a very effective featureizer for natural images. However, on medical images like X-rays and skin lesions, they found they are perform worse than pixels, which means they do not have strong priors about how to correctly get features from those medical images. So without the guidance from those priors, so the model can only rely on the data to learn the parameters. And in medical, the data are in small scale and biased. So the model may just overfit on some spurious correlations in the data and cause them to have catastrophic failures when tested in a different scenario. So how can we incorporate more priors to the system? Our work is inspired by how medical students are educated. So medical students will first stay a few years in the medical school to learn some clinical knowledge from textbooks. Then they will be sent to hospitals to do some residency to actually practice on some cases. But previous work mainly skipped the first step and only rely on the data to learn the model. So our work will try to incorporate the first step. So we try to incorporate priors from medical documents and use a retrieval augmented generation method. So we will query like using the disease we want to classify, for example, like COVID, and we will retrieve documents from some medical corpus like PubMed, which contains a lot of medical articles. And we retrieve some relevant documents, which will be used as context for a large language model to generate some concepts. And we can use some other disease as a query, or you even use the concepts as queries to iteratively build our knowledge priors. With such knowledge priors, we can again use the concept bottleneck ideas. So we get priors from the medical documents. Each knowledge is like a binary question about some clinical knowledge that doctors will actually use when they diagnose some disease. And we will ground the input image on those knowledge and then send them to the linear layer to make the final label prediction. And we found that using this way, we can get a more robust model. So we compare with black box models like Vision Transformer and show the average performance on 10 confounded datasets. So Vision Transformers, they can achieve high performance for in-domain, but for out-of-domain, it will decrease a lot, with over 60% gap across those domains. While for our knowledge bottleneck model, we sacrifice a little bit on the in-domain performance, but we achieve much higher out-of-domain performance with over 30% improvement comparing to Vision Transformer. So in this case, we obtain a more robust model using knowledge priors. So to sum up this work, we try to include knowledge priors from medical documents through this interpretable structure, and we can achieve better robustness for medical AI. Any questions? I cannot see the chat.
Yeah, I can ask a quick question.
Okay.
I'm curious to understand the drop in the in-domain examples. The drop isn't too much, but did you do any analysis to understand why the drop happens and what you can do to mitigate it?
The drop, because in those confounded data set, we use different confounding factors like race or different hospitals or the sex of the patient and even different views. And we also test on like skin lesion images, like different skin color, dark skin and light skin. So the model is easily just overfit, just rely on those shortcuts to achieve high performance. It's just like, because this ERM method, like it just minimize the loss of the in-domain function, but it's easy to use those bias to find a simple solution here. So that's why vision transformer will have such a big drop. But using our way, we constrain the model to only rely on medical knowledge to make the diagnosis, rather than just like those demographic variables. So we can achieve better robustness. And I think we incorporate include some other baselines in the system in the paper, and it's hard to mitigate these issues. The model still, like those black box models, still overfitting on the data, and our knowledge bottleneck is just much more robust. Yeah.
Got it. Thanks.
Yeah.
Yeah. And I was going to ask, is the only part of the model being trained this linear layer?
No. Actually, in medical domain, we also we cannot rely on clip for grounding knowledge and image, because the foundation models in medical domain is not reliable. So we instead train the individual binary classifiers for each concept here, rely on a big multimodal data set called Mimic, contains a lot of clinical report and x-rays. So we fine tune classifiers for each on each question here. So it's more robust. Yeah.
And
the linear
is that trained on the in-domain data or
no,
more general data?
It's a pre-training data set used usually to pre-training the medical clip. Yeah.
So then the linear layer is what you tune on the in-domain data?
Yeah, we have other downstream tasks. Those data sets, those county data sets are built from a lot of different X-ray data sets. Yeah.
I had one quick question if we still have time.
Yeah. Yeah.
Yeah. I'll try to make it quick. So for the vision transformer, you're also providing those confounding, not the confounding, you're also providing those descriptions of the data sample, like the age and the sex, as a separate value, or is it just embedded in the image?
Embedded in the image. So the task is classify disease, not for demographic variables. So, yeah.
Okay, so when you said the demographic variables are available, that's extracted by the transformer, not necessarily provided separately.
We did not provide it. We just use that to construct the confounded data sets.
Got it. Thanks.
Okay, great. So I think this work is a good example to answer an open question for the explainability community, that why do we need interpretable models? If the black box model is perform well on some task, why we need interpretable structure? But in this work, we show that it can bring us robustness in those critical domains. And I also want to show another example of interpretable method, which is a paper we recently got accepted to Nature Communications last week, where we collaborate with a hospital in China, which is specialized in ophthalmology to detect some eye tumor, very rare eye tumor disease. It's pretty rare, only happens for 5 people every million, but has high death rate. Without any treatment, this cancer can transfer very quickly, and the average survival rate for patient is around 4 to 12 months. And compared to black box models, which can only provide doctor the final label, our concept bottleneck models can also show the doctors the top concepts. So that gives some rooms for doctors to incorporate those AI generated predictions into their final diagnosis. So we found it can improve the performance of junior doctors. So for this rare disease, it requires a lot of years of experience to correctly identify those diseases. So senior doctors can do pretty well, but juniors is still like a big gap with senior doctors. And we found combine junior doctors with CBMs, we can achieve the similar level of senior doctors' performance. So far we talked about how to use language as model structures, and we showed 2 bottleneck work which can improve the interpretability and robustness of AI systems. And in the next, I will show from the data angle, how can we use language-guided synthetic data to improve the data efficiency in vision language models and embodied AI. So we've seen great success of scaling language data to build strong large language models, but compared to the size of language data, the data size of some vision-related tasks is still small in scale, like this robotic transformer took 17 months to only collect 130K episodes. Although we have relative large-scale image text data, but the quality is not good enough. Like the text is just the alt text of those images. They may be useful to train some alignment model like CLIP, but if we want to build a more advanced vision language reasoning model, those data is not good enough. And we propose whether we can use the priors we learned from language data to improve data efficiency for those vision tasks. And here, I just want to show two examples here. First is using code-guided generation to build synthetic text-rich images to improve vision language models' ability in understanding like charts, documents, tables, etc. And this is part of the effort for the MOMO project. And second, I will show the how can we use language models to build 3D environment to build more generalizable embodied agent. So let's start with vision language model, which has largely converged to this architecture where we rely on a language model as a backbone and connect the visual feature to the textual space through a connector. However, such architecture has some imbalance problem, like we always have a very large language model. So if we don't have high quality image text data to properly train the model end to end, the model may just ignore the visual input or don't know how to process the visual input and leads to some problems like hallucination or overfitting on some benchmarks. And one important application of those vision language models is to help us to understand text-rich images like documents, charts. We use them a lot in our papers and in other fields, and this can automate some data analysis. And the community is really lack of such data. So how do I know? It's interesting to find that the Pixmo docs, those synthetic text-rich images, is now the most downloaded and most liked data set in Pixmo. And there are some limitations for existing data sets. So first, they are not very realistic. They use randomly generated values and labels, so lack of meaningful semantics. And they are lack of diversity. They have limited types of figures and sometimes use template-based questions. And also they have limited supervision. They only annotated with a short answer, but usually to answer such question requires multi-hop reasoning. So without the rich annotations, the models may just overfit on the annotation bias of this data set instead of learning how to correctly understand those figures. So to address these limitations, we start with the motivation that those text-rich images are usually generated from programs. Like we use Python to write charts, we use LaTeX to generate documents, we use HTML to render web pages. And large language models have been shown to be very good at writing code. So how about we just using language model to generate those synthetic data? And another motivation is that the textual reasoning ability of large language models is still more advanced than the visual reasoning of those multimodal models at current stage. And we can show that by asking models to answer a question about a table. We can use the text input like the markdown format for a text-only large language model to answer the question. We can also render it into an image using vision language model to answer the same question. And on the wiki table question dataset, we found there's a significant gap when using different modality as the input. And we wonder whether we can use leverage the textual reasoning ability to improve the visual reasoning ability of multimodal models. So based on those motivation, our high-level idea is to use code as the intermediate representation. So we will prompt a large language model to generate code. From code, we can get the image data. And use code as context, we can again let a text-only language model to generate some natural language instructions like question and answers. And we can use those synthetic data to train our vision language model to improve its ability in understanding those figures. And based on this idea, we built a code-guided synthetic data generation system. The input to the system is a type of image you want to generate. Like I want to generate like a book cover, and it will output a multimodal data set with corresponding data sets and instruction in tuning data for your to train your vision language model. So here is a general workflow for this system. So given the input, like I want a data set of book covers, and we have 11 rendering tools which support 20 pipelines to generate like charts, documents, tables, even some specialized domains like music sheets or some chemical structures. And for example, here we choose HTML. It will start with topic generation. And to further diversify the content and styles of the data we generated, we use this persona-driven approach, which will sample a persona from the 20K personas we have. Each persona is one sentence to describe the personality of or identity of a person. And we condition on this persona to generate a customized topic for this persona. Like, for example, here, a sci-fi novelist, we have a generated topic, which is about a novel about some alien world. And this will also affect the data we generated. And finally, we can get the code to generate this synthetic data. From the code, we can run it to get image. So you can see it's conditioned on the persona here. And use code as context, we can generate instruction tuning data. And using this system, we build a large-scale synthetic data set with 400K images, including charts, documents, math questions, tables, diagrams, vector graphics, music sheets, electrical circuits, and chemical structures. So to show that those synthetic data can truly benefit vision language models, so in our experiment, so this is an earlier version of mobile, which we use Mistral 7B as a backbone and use Clip as a feature extractor. And what we mainly want to show here is for the supervised fine-tuning data. And here we have different categories of supervised fine-tuning data. First is the evaluation data set. Those are some benchmarks we want to test our models, but they have some training data which can be used for the supervised fine-tuning. We can also grab some other academic data set for auxiliary training, some multitask data sets. And finally, we have our synthetic data. So our best perform model will use all three categories of data sets, but we can also just use the auxiliary data and synthetic data to get a zero-shot model because we did not use any samples from the evaluation data set. And for the baselines, we compare with open source models in like 7B to 12B scale and also some proprietary models. And here are the main results on those 7 text-rich benchmarks. We found that our 7B model achieved the top 1 performance and can outperform the second best, the Llama 3.2 11B by over 3%. And more surprisingly, we found our zero-shot model, which we did not use any instance from the evaluation benchmarks, can achieve very high performance. It can outperform most of the open source and closed source models. This demonstrates the effectiveness of the model learned from the synthetic data. They can be real transferred to some real benchmarks. And here is a detailed breakdown of performance on each individual dataset. Our model can consistently outperform GPT-4b. And when comparing with the best numbers for each dataset, we achieve top 1 performance for 4 datasets out of the 7 datasets. And for the rest dataset, we can also get a very competitive performance. And to further quantify the performance gain we get from synthetic data, we did this ablation study on different choices of supervised fine-tuning data. So to recap, we have auxiliary data, we have synthetic data, we have the training data from the evaluation benchmarks. So if we don't use the training data from evaluation benchmarks, we get a zero-shot model. So on the zero-shot settings, if we only use auxiliary data, use those academic data sets, even after training over 1 million images, they still cannot perform well on those testing benchmarks, has a significant gap with GPT-4b. But if you only use synthetic data, you can already achieve similar performance as GPT-4b. And when combining these two, our zero-shot model can outperform GPT-4b. You can easily outperform GPT-4b by just make a supervised model using the evaluation dataset. But including auxiliary data, it won't improve a lot. Even after adding another 1 million data, it's just only improve like 1 or 2%. But including synthetic data, you can further boost models' performance. And here is the, for each data set, we show that adding synthetic data can consistently improve models' performance. From previous experiment, we kind of found those vision language models have limited generalization ability. They always require in-domain data to perform well on some tasks. And when given a novel task, like answer a question about a nutrition fact, if the model haven't seen such data during training, it may struggle on it. However, with our code-guided synthetic data generation systems, we can synthesize task-specific data, like we can synthesize synthetic nutrition facts to fine-tune your vision language model to perform better on this task. To show these stories too, we collect an evaluation dataset called Nutrition QA, which contains 100 examples. Those are photos I took in some grocery stores, and we annotate some questions. Some of them requires multi-hop reasoning. And we evaluate those open source models' performance, their zero-shot performance on this Nutrition QA dataset. And to quantify the data efficiency, I set the x-axis here is the instruction tuning data size, which is the number of training data they use during supervised fine-tuning stage. So you can see most of those open source models lies on the lower right side, which means they use a lot of data but still cannot perform well on this new task. Even a lot of those models claim they can achieve GPT-4V level performance, but when tested in the wild, when tested in some novel task, GPT-4V is still very performant. And our model, without using synthetic data, achieves similar results that we use over 1 million data and still cannot perform well on this nutrition QA. While our model only using the synthetic data, we can achieve similar performance as GPT-4V. And more importantly, since our generation system can generate task-specific data, we can only generate 7,000 synthetic nutrition labels for the entire supervised fine-tuning stage. We can already achieve very decent performance, and this is very data efficient. So those vision language models has limited generalization ability, and synthetic data is an efficient way to bridge this gap. So next is new results I got recently, which is we can generate pointing data through synthetic data generation. Like here are some synthetic pointed data I get. So the method is like, since we have the original code to render the image, and we can prompt a large language model to generate a pointing question, like given this menu, the question is point to the vegan options. And since we have the code, we can use large language model to modify the code to actually draw a point on the image. So we render the edited code, we let the model to actually draw a point on the image. And we can also let it know which kind of color, like we can use this AI to pink color to draw the point. We can simply draw a mask on this image. And then we can extract the coordinates of those points. And then we can use those synthetic pointing data to train your vision language model to do pointing task. And to show that those synthetic pointing can generalize to some real tasks, I annotate a dataset called DocPointQA, contains 300 examples from DocQA, which contains some handwritten documents or photos of documents. And when tested on this DocPointQA, we compare with Pixmod point, like the model, this is human annotated pointing data. And we found models channel Pixmod point cannot well transfer to those DocPointQA. But with synthetic point, even much smaller size of data, we can achieve much better performance. And combine those two pointing data, we can further push the performance. So I think this experiment suggests that we can also use this synthetic pointing data to do some agent tasks in the future. So for the final part of the talk, I will talk about Holodeck, where we use language-generated simulated environments to build more generalizable embodied agents. And previous work mainly relies on human-designed environments to do these sim-to-real tasks. And those have limited diversity and scale, which will also constrain the ability of the agents. So we started with the motivation that a language model contains the common sense knowledge about how to design those environments. And like we can prompt like how to design office, it can give us some high-level natural descriptions. And the challenge is how to convert those high-level language description into a interactive 3D environments. And here we present Holodeck, which can take language as input to generate interactive 3D environments to train your embodied agents. And here the input is like a fan of Star Wars, so we can have R2-D2 and Stormtrooper in the room. And you can also visualize these environments using your VR headset to give you some immersive experience. And Holodeck can generate diverse environments, not limited to residential environments, like we can generate arcade room or spa. You can also customize the styles of the room, like I want a bohemian style. The main idea of Holodeck is to do procedural generation with large language model, but here each procedure is controlled by a large language model. So given the user input, like I want an apartment of a researcher who has a cat, it will start with the floor and the wall module to design the floor plans, and then the wall and door and window module will install doors and windows. And finally, the object selection module will select appropriate objects for each room and customize based on users' input. Like here we have a cat climbing tower because the input is a researcher who has a cat. And finally, the layout design module can generate, put them in the right place to make sure they are arranged coherently in the room. And each module is follow this paradigm, like from high-level input, like users' input, we can get some natural language descriptions, and then we write some functions to convert those high-level information into more structured, like in JSON format for the Unity to render the environment. And with large language model to control each module, we can have customizability in each step of generation. Like we can customize floor plans, we can customize materials, and we can customize doors and windows. Like for a disabled person who needs to use a wheelchair, language model will choose to use wide doors. And we can rely on observers. We can also customize the assets in the room. And one immediate application of Holodeck is to build more generalizable embodied agents. So we designed this zero-shot object navigation in novel environments, such as a music room. And there are some novel objects like piano. So if the agent haven't seen such environment or those objects during training, it may struggle on it. But with Holodeck, we can synthesize some synthetic music rooms to fine-tune the agents to perform well on those novel environments. And we ask some human experts to design testing environments, including like daycare center or office or arcade room. And we found that Proxol, the agent pre-trained on Proxol, achieve similar to random performance. But after fine-tuning our Holodeck, it will boost the performance. And this improvement is also comes from the language price, because we use language model to design synthetic environments that's closer to the testing distribution. Question?
Yeah. So for this, in the novel environment, what would be the target type, target object type to the agent? Is this like unseen in the Proxol, or is all of them unseen in the Proxol training?
It's seen in Proxol because this Proxol version is using observer's assets. So it may have seen such object types. But in Holodeck, I think it's just a different distribution. We know what are the testing environment will be like. We will generate synthetic arcade room, which will have higher chance to have the similar objects that we will see in arcade. So the agent is always seeing similar objects during training. So the distribution is closer here.
Yeah, that makes sense. And how is this open vocabulary, or do you have a set of target object type?
We have a set of
test?
object types. We have around 60 object types. Yeah.
Gotcha. Thank you.
Yeah. So I think it's close to the end of my talk. So in this talk, I mainly talk about how to use language priors to build better visual intelligence through different aspects, like language as model structure. We show this bottleneck structure can improve the interpretability and robustness of vision systems. We also show that language can help generate synthetic data to improve the data efficiency for vision language models and embodied AI. So for the last two slides, I want to talk about my future work. So we've seen great success in AI for general domains, but I think in the future, to make those models truly benefit our world, we need to apply them in critical domains, in high-stake domains, to those domains that can truly saving human lives. So one goal of my future research is to apply trustworthy multimodal intelligence in those critical domains. And this requires not only consider the model's performance, but some other aspects of our model, like the safety, the robustness, whether we can incorporate domain knowledge in the system, and how can we interact with those models to fix the mistakes to just achieve better performance. And all those requires us to have better controllability to the AI systems. And I believe interpretable structure is a promising way to achieve those goals. And second, looking back to my PhD journey, I did a lot of image classification where we teach the model to perceive the world. For now, we have vision language models that can do some reasoning. But for the future, to make them truly applicable in the real world, we need them to act in the environments. So another research goal for my future research is to build generalizable multimodal intelligence that can interact with the real world. And this includes two directions I'm excited for. First is multimodal digital assistant, that how can we teach agent to do some daily tasks in our computer environments. And second is to build foundation model for embodied agents that can make them to navigate and interact with some novel environments in our world. And I believe all those can be achieved through synthetic data. And I would like to thank you for listening. And I would like to thank all my awesome collaborators for the work I presented today. And I will leave time for question and answers. Okay, Chris. Mm-hmm.
So I had two questions. So on the synthetic document data,
Mm-hmm.
were you using the explanations in those experiments?
Yes.
Or just the short answers?
Yeah, I have backup slides for that. Yeah, we do use explanations, and I found interesting results, which is those explanations may benefit. Can you see my screen now? These slides. Okay.
Yeah.
So using explanations will help on some of the data sets like chart QA, table QA, nutrition QA, because those data sets, some examples requires multi-hop reasoning, and adding explanations, we can let models to do chain of thought. But for some other data set like doc QA, info QA, adding chain of thought will hurt the performance because those data set requires model to answer as few words as possible. Adding chain of thought will make your answer more natural language. But since we are using string matching matrix for those data sets, so for example, like here, you can see adding chain of thought, the answer becomes like Tuesday and Thursday, ground truth is T2TH, but we got a 0 score. But actually this prediction is correct. So there are some answer bias in those academic data sets.
Yeah, interesting. Mm-hmm. And then in your future work, you said we can achieve this through synthetic data. Do you mean purely synthetic data, or like synthetic data plus human collection, or yeah, how far do you think we can go with just synthetic data?
Yeah, I think we definitely need to combine human data with synthetic data. But I think human data has some limitations. There are some copyright issues. It's hard to scale and hard to collect. It's very time consuming and costly. Synthetic data is a more controllable way. We can generate the data we want. Like if we want to teach the model which kind of capability, we can generate target synthetic data for that domain. So it's a very controllable way. But I think we still need to get diverse data from the human, like from the human feedback. This may truly improve the usability of the model. But more specifically for some agent tasks, I think it's a very natural way to use synthetic data because those are done in some simulated environments in our laptop. So it's easily to get synthetic data out of those environments. So I believe it's a very promising way for those kind of tasks.
Yeah, so in your future work, you mentioned that you believe the synthetic data is the key to embody this intelligence model, like to interact with the environment. What kind of what kind of interactions you are considering in this aspect?
Yeah, I think this maybe we can use a different word for embodied AI. example is more like simulated environments. And I think in the simulators, we can do a lot of tasks like manipulation, navigation. And I think since if we have more realistic environments, the gap between simulation and real world is smaller. So we can teach the model to do a lot of tasks in our simulators, and hopefully it can be well transferred to the real world. So I think if we develop very robust and realistic simulators, it is very promising to show that we can transfer those skills learned from simulator to real world, to interact with the real world.
So in terms of realistic or like more close to a real world, do you mean the appearance, texture, or the physics simulation?
Yeah, all those things like physics, appearance, those like fidelity. Yeah.
I see. Okay. Thank you.
I have a related question as well. You talked about controllability and interpretability being important for controllability. I was wondering if you could maybe explain why. I'm thinking about even something as simple as control net, which is an uninterpretable model, but it does afford some amount of controllability. Do we really need interpretable structures built into the model?
Yeah, I think control net is a good example here, but I feel that's still for the general domain. Actually, we just want to control the model to do some different task, not for some other properties. But I think for healthcare, for some high-stake domains, we need to have a tool to kind of know what the model is doing. And when the model is making mistakes, we can have a way to correct its mistake. And I think interpretable structures just giving human a way to look at what the model is doing and to interact with the model, to just have better control over the model's behaviors. And I think that's an important property for those critical domains.
Could you maybe walk us through a type of error correction you might expect in a critical domain?
Okay, let me have
especially since I think you had some examples with the concept bottleneck stuff as well.
So for example, one interesting example we come across in doing those healthcare applications is that it can help us to identify some biases in the data. So if the bottleneck we found that the model designer concepts is using like using sex or using race or using some other demographical variables in the concepts, and it has a high impact on model when making the decisions, we can actually we can identify that concepts, and we know there are some biases in our data, and we can remove that concepts. That will force the model to rely on knowledge rather than some confounding factors. So that's a way to correct some models' behaviors. That's one advantage. Another thing is in this experiment, when we want to use AI to assist doctors, we also did another experiment, which is to combine junior doctors with a black box model. Actually, adding black box models with junior won't improve a lot on junior, because the doctors may just don't believe the model's prediction because it's just a final prediction. There's no other explanations. But using interpretable structure, we can give richer information for the doctors. Like doctors will know what are the top concepts for this case, and doctors can incorporate those information into their decision process. And we found that using this way, it can better assist doctors in those clinical process.
So you talked a little bit about synthetic data for agents.
Yeah.
And one challenge there could be that a lot of agentic behavior that we want to see, like we don't know how to generate that kind of data, right? So error corrections and like trying to get out of sticky situations and things like that. Even if you think about coding as a use case, how are you thinking about dealing with those while generating your synthetic data?
Yeah, I think this kind of I think those agent tasks requires different skills of the agent. And what you mentioned, like stuck in some step and we need to like some critics. And I think that's still some reasoning ability of the agent. But I feel for the synthetic data I want to build, it's more like some taking the visual input of your screen and know where to click and know where to type in. Those kind of parts can be used to generate synthetic data. I think that's easier to generate. Maybe we can come up with better ideas to generate more complicated steps in the agent task. And I think one experiment I'm trying to do, because I haven't got my access back, is like how those synthetic pointing data can improve the click success rate on those agent tasks. Because in a lot of tasks, you need to click the some different icons on your laptop. And I think this kind of task can be improved using synthetic data. But what you mentioned maybe is more about the language ability or about the some long chain of thought reasoning ability of the model. And I think that can come from the language model.
And since you mentioned chain of thought, have you tried doing this chain of thought with your language bottleneck idea? So the same model produces the answers to the questions as chain of thought and then predicts the final answer. And does that help?
I think for our language bottleneck, we're still doing some image classification task. It's not about some generation task, but I've known there are some other work try to use this bottleneck in a generative model to guide the control the generation of the model. So I think maybe in those kind of tasks, adding chain of thought may help. Yeah.
I see.
Okay, I think we're at the time. So if there's no other questions, we can end here. But yeah, thanks for the great talk, Yue.
Thank you, everyone.